Hey guys, Mr. B here, and this video is going over the Chapter 3 review guide. Alright, let's begin here. Number 1, it says solve the following and express each answer in scientific notation and the correct number of significant figures. So basically all we're going to do here is we're going to plug these numbers into our calculator, we're going to get an answer, and we're really just looking to round the proper number of sig figs. So 5.3 times 10 to the 4th plus 1.3 times 10 to the 4th. We get 66,000, but again, we want to round this to the proper number of sig figs, and we want to put it in scientific notation. So, sig figs wise, there should be 2 sig figs, or sorry, not 2. We want to have 1 place after the decimal. We are doing addition here. So we want to round this to 6.6 times 10 to the 4th power. Because again, the decimal is, actually let's zoom in a little bit here. The decimal is here, and we want it to be between the first 6 and the second 6. So to do that, we have to move it over 1, 2, 3, 4 places, and this then should be our final answer. All right, next one here, 7.2 times 10 to the negative 4th divided by 1.8 times 10 to the 3rd. So again, let's do this on our calculator here. Divide by 1.8 e to the 3rd, and we get 0.000004, and we want this to have 2 significant figures, so we are going to move the decimal place so that it's 1, 2, 3, 4, 5, 6, 7 places over, so we're going to get 4.0 times 10 to the negative 7th, and it's going to be negative because this number is smaller than 1, so we have a negative exponent in this case instead of a positive 1. All right, let's do one more here real quick, and then I'm going to let you do D and E on your own just because to save some time. So let's do letter C. We've got 1 times 10 to the 4th times 1 times 10 to the negative 3rd times 1 times 10 to the 6th. And I get as my answer 10 million. And this should have only 1 sig fig because this has 1 sig fig and this has 1 sig fig and this has 1 sig fig. So we're going to round this just to 1. So our final answer is going to be 1 times 10. And again, the decimal is technically there. So we have to move it over 1, 2, 3, 4, 5, 6, 7 places. So 1 times 10 to the 7th should be our final answer. Okay? All right. Again, I'm going to let you do D and E on your own, but if you do have questions on those ones, you can always email me or ask me and I can show you. All right. Looking at number 2, it says the boiling point of octane was experimentally determined to be 124.1 degrees Celsius. The actual boiling point of octane is 125.7 degrees Celsius. Calculate the error and percent error. Okay, so our experimental value in this case is going to be 124.1 Celsius because they do tell us that this was experimentally determined. And they tell us that the actual boiling point is 125.7. So our actual value, or sorry, our accepted value is 125.7 Celsius. So our error, remember, okay, so error is going to be experimental value minus accepted value, which is going to be 124.1 minus 125.7. So we get 124.1 minus 125.7. 124.1 minus 125.7. We get an error of negative 1.6. And then for our percent error, we're going to take the absolute value of that. So basically just take it as a positive. Okay, so percent error is the absolute value of our error. And then our error, there we go. And we're going to divide that by our accepted value. And then we're going to times that by 100 to get it to be a percentage. Okay, so this is going to be absolute value of 1.6 divided by accepted value is 125.7, and then we're going to times that by 100, and we should get a percentage. So 1.6 divided by 125.7 times 100, and we get a percent error. And let's round this to, I guess, 4 significant figures. We get 1.273% as our percent error. There we go. Okay. All right. Number 3, as a result of experimental work, a student finds the density of a liquid to be 0.1369 grams per cubic centimeter. The known density of that liquid is 0.1478. What is the percent error? All right. So we already have all the equations and stuff up in the previous one. So percent error in this case is going to be equal to our error. So this is going to, we'll just do it all in one go here. So this is going to be 0.1369 minus 0.1478. Okay. That is our experimental value minus our accepted value, and then divide this by our accepted value of 0.1478, and then times this, oh gosh darn it, there you go, sorry, times this by 100 equals, okay, so let's see, 0.1369 minus 0.1478, and it is going to be a negative, but remember we're going to take it as a positive because of absolute value, and divide that by 0.1478 times 100, and we get a percent error, and we'll round this to 4 significant figures, 7.375%. That's our percent error, 7.375%. Okay, number 4, determine the number of sig figs in each of the following. All right, so we're just counting sig figs. The first one, not a decimal, so all of these non-zeros count, so 1, 2, 9, and 1, so there's 4 sig figs. Then these 2 zeros, which are sandwiched, count as well, which means this one has a total of 6 sig figs. Letter B, this one is a decimal, so we're going to count starting from the left. We're going to move our way in, and the first digit we hit that's not a 0 is the 8. Everything after that automatically counts, so that is 3 sig figs. Letter C is 100 decimal grams. This one's kind of weird, but it is a decimal. So the first number right away is the 1. That's our first sig fig, and then the zeros automatically count after it. So that is 3 sig figs. Okay. Now, if it was just 100 with no decimal, it'd be 1 sig fig. But the decimal gives us 3 sig figs. Okay. Kind of a weird little thing to add on there, but it does change the number of significant figures. So letter D, we have a total of 6 sig figs. And letter E, we have a total of 1 sig fig. All right, number 5, how are accuracy and precision evaluated? So this is basically just saying, like, what is accuracy, what is precision? This is directly from the notes. So remember that accuracy is a measure of how close one measurement, or of how close a measurement is to an accepted or true value. Okay, so accuracy is a measure of how close a measurement is to, like, a reference or a true or accepted value. And precision is a measure of how close a series of measurements are to each other. Okay, so accuracy is like how close is one measurement to the accepted value. Precision is more about how are these measurements, to all these multiple measurements, how are they in relation to each other in terms of how close they are. So, all right. Number 6, solve each problem with the correct number of sig figs. Okay, so we're not going to do all of these, but I'll maybe do like every other one. So we'll do A, C, E, and G. And we're just going to do some basic math and then round to proper number of sig figs. So for letter A, we have 8.3 times 2.22. I get 18.426, and this would be squared meters. But we need to round this to the right number of sig figs. Since this is multiplication, we need to count how many sig figs are in the measurements we used. So 8.3, that's 2 sig figs. 2.22, that's 3 sig figs. Seeing as this one then is only 2, our answer needs to be rounded to 2. So it means we're going to keep the 1 and the 8. The 4 will keep the 8 and 8, which means our final answer should be 18 squared meters. Okay, rounded to 2 sig figs. All right, letter C, 35.2 times 1 minute over 60 seconds. So it's basically 35.2 divided by 60. Okay, so 35.2 divided by 60. And I get as an answer 0.5866667. This would be in the units of minutes. Now, again, we don't want to keep this whole number, so we are going to only use this 35.2 seconds to determine our sig figs. And the reason why we're not going to use this part here is this is a constant. Okay, this is a conversion factor, and constants or conversion factors don't have sig figs because you're not estimating anything. Okay, like 1 minute is exactly 60 seconds. There's no estimating there, which means if there's no estimating, then there's no significant figures. So we're only going to round this to 3 sig figs, which means we're going to keep the 5, the 8, and the 6, and then this 6 will round that 6 up to a 7. So our final answer here will be 0.587 minutes. Okay, this is going to be our final answer with 3 significant figures. All right, letter E, 9.44 minus 2.11. So 9.44 minus 2.11, I get 7.33 meters. And since this is subtraction, we're going to look at how many places after the decimal do each of these have. Each one has 2, which means you just need to round our answer to 2 places after the decimal, which we already have. So this is just going to be 7.33, and that's it. Piece of cake. All right, lastly then, letter G. We have 34.61 minus 17.3, and I get 17.31 meters. Now this first number has 2 places after the decimal, and the second one only has 1 place after the decimal, which means our answer has to be rounded to 1 place after the decimal, which means that our final answer will be rounded to 17.3 meters. Okay? All right, moving on. Number 7, which 5 SI-based units are commonly used in chemistry? This is directly from the notes, but we have for mass, kilogram. We have for volume, the cubic meter. We have for time, the second. We have for, I think, amount is the mole. And then, I'm trying to remember what the last one was. Ooh, we're going to have to go look. I don't remember off the top of my head. Let's go take a look here. Chapter 3, Section 2. What is the last one? This is, by the way, this is why we use our notes, guys, because we can. The last one is the Kelvin for temperature. There we go. All right, so the last one is temperature, and that is the Kelvin. See, even I don't remember all of them sometimes, okay? I got to use my notes as well. So use your notes. It's okay to do that. All right, number 8. Which metric units are commonly used to measure length, volume, mass, and temperature? All right, well, we pretty much just did these ones. So we have length, which is the meter. We have volume, which is the cubic meter. We have mass, which is the kilogram. And we have temperature, which is the Kelvin. So, all right, number 9. What is the symbol and meaning of each prefix compared to the base unit of the gram? So this is basically just asking what's the symbol and the meaning of each one. So milli, symbol is M, lowercase m. The meaning is 1,000 times smaller. Nano, the symbol for this one is a lowercase n, and this one means a billion times smaller. Deci, this one is a lowercase d, and this one means 10 times smaller. And for centi, this one is a lowercase c, and this one, not a copyright symbol, just a lowercase c, and it means 100 times smaller. Okay, these are directly from the notes. There's a chart that you can look at if you don't know those ones. So again, remember for the test, you do need to know these prefixes. Okay, I'm not going to give them to you. So if you need to make flashcards or something to remind yourself or remember them, do so. But you need to know them. They're not that complicated. Okay, so number 10, list the following units in order from largest to smallest. All right, so we got kiloliters, milliliters, centiliters, microliters, regular liters, and deciliters. All right. So the smallest one we have here are microliters. Okay. Oh, I'm sorry. We're ordering from largest to smallest. So largest is the kiloliter. Then from the kiloliter, the next largest is the regular liter. Then after the regular liter, we have the deciliter, since that is 10 times smaller. Then we have the centiliter, which is 100 times smaller. The milliliter, which is 1,000 times smaller. And last, we have the microliter, which is 1,000,000 times smaller. Okay, so just to make sure that we know, largest is kiloliter, smallest is microliter, and all the ones in between. Okay, and again, this is just using the prefixes for the metric system, which again, you can find in the chart in chapter 3.2. All right, number 11. What is the volume of a paperback book? 21 centimeters tall by 12 centimeters wide by 3.5 centimeters thick. So volume for a book is going to be length. Oh, it's going to be length times width times height. So we're going to have 21 centimeters times 12 centimeters times 3.5 centimeters equals, so 21 times 12 times 3.5, and we get 882, and it's going to be cubic centimeters because centimeters times centimeters times centimeters, but we need to round this to two significant figures because of the numbers that we use to calculate it, and this currently has 3, so properly rounded, this is 880 cubic centimeters, right? 880, that is our answer. All right, 3.3, number 12. How many milliliters of gasoline are in 12 gallons of gasoline? All right, so this problem, we are starting with gallons of gasoline, and we're trying to convert into milliliters. Now, they do tell us that 1 gallon is 3.78541 liters. Okay, so they are giving us a conversion between gallons and liters. However, that doesn't get us into milliliters. That only gets us to regular liters. So first up is going to go gallons to liters. And after we get into liters, we can go from liters to milliliters. And just to know what that is, we need to know, of course, the conversion between liters and milliliters. But milliliters, milli, means 1,000 times smaller. So there are 1,000 milliliters in 1 liter. Okay, so that's the other conversion factor. So let's set up our conversion. We have 12 gallons of gas, and we can put it over 1 if you want to make it a fraction. And the first conversion, we're going to go from gallons to liters. We're going to use the conversion factor that they're giving to us in the problem, We'll have 3.78541 liters on the top, and we want to have the 1 gallon on the bottom because we have gallons here. We want to have the same unit on the bottom so that they cancel out. So gallons will cancel out like this. And then from here, now we have the units of liters. And then we want to use the 1,000 milliliters per liter to then convert this into milliliters. Okay, so we're going to have 1,000 milliliters on the top. And on the bottom, we will have 1 liter. That way we have liters here, which will cancel with liters there. And then when we do all the math, we will have our final answer in the units of milliliters, which is what the problem wants because the question is asking how many milliliters are there. All right, so all we need to do then is take 12 times 3.78541 times 1,000, and I get 45,424.92 milliliters. And then we are going to round this to two significant figures because this 12 gallons here that we began with only had 2 sig figs, and these other numbers have more. So 2 sig figs means we're going to keep the 4 and the 5, and then this 4 is going to keep that 5 of 5. So this is going to round down to 45,000 milliliters. Okay, that's 2 sig figs. 4 and the 5 are the 2 sig figs. The zeros don't count because there's no decimal and they're not sandwiched between anything. So there's our final answer, 45,000 milliliters. All right, number 13, how many nanoseconds are in 40 hours? Okay, so we're going to go from hours. Now, I don't know if you know how many nanoseconds are in an hour. I certainly don't. So here's how I'm going to think of it. I'm going to go from hours to minutes because I know that there's 60 minutes in an hour. Then I'm going to go from minutes to seconds because I know there's 60 seconds in a minute. And then I'm going to go from seconds to nanoseconds because there are a billion nanoseconds in 1 second, because nano means a billion times smaller. Okay, so we're going to do this in 4 steps or 3 steps, I guess, however you want to think about it. But we will start with 40 hours. Again, if you want to put it over 1 to make it a fraction, you can. And our conversions are going to be, let's just write them all out so we can see them here. Okay, so we have 60 minutes is equal to 1 hour. There's the first one. Then we have 60 seconds is equal to 1 minute. There's the second one. Then we have a billion, and I'm going to do it in scientific notation just to save myself some space. So 1 times 10 to the 9th nanoseconds is equal to 1 second. Okay, so the first conversion, we're going to go from hours to minutes. So we're going to use the 60 minutes over 1 hour, because we want hours to cancel with hours. Okay, so that's this first conversion here. Then from there, we're going to convert our minutes into seconds. So we're then going to have 60 seconds over 1 minute. That's fine. We'll keep it crossed out. So we're going to cross out this one here. So minutes cross out. So that's this conversion here. That one's done with. And then our last one is going to be converting seconds to nanoseconds. So we're going to have 1 billion. So 1 times 10 to the 9th. Oh, geez. What am I doing here? Times 10 to the 9th nanoseconds. And on the bottom, we're going to have 1 second. So that these seconds will cross out with these seconds. Okay. And then finally, we'll have an answer in the units of nanoseconds. So we're going to take 40 times 60 times 60 times a billion. And we are going to get a very large number. So let's see here. So let's go 40 times 60 times 60 times a billion. Wow, it's a big number. Okay, so we got 144 and then 000, 000, 000, 000, 000 nanoseconds. And I guess since this is 40 hours and that's 1 sig fig, we'll round this to 1 sig fig. So basically we're going to have the decimal, which is there. We're going to move it to there. And then that 4 is going to keep the 1 a 1. So let's do this in scientific notation. So we're going to have 1.0 times 10. And in this case, we have to move the decimal over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 places. So times 10 to the 14th nanoseconds. All right, so there's our final answer with the right number of significant figures. And we're going to do it in scientific notation just to make it smaller. So, all right, number 14. An experiment requires that each student use an 8.5 centimeter length of magnesium ribbon. How many students can do the experiment if there is a 570 centimeter length of magnesium ribbon available? Okay, so they're telling us right at the beginning that one student is going to need 8.5 centimeters of ribbon. Okay, it's conversion factor. And we are starting with 570 centimeters total. So we're going to convert 570 centimeters into number of students. This is just going to be a one-step conversion. And the conversion factor we're going to use is the one given to us in the problem. So one student over 8.5 centimeters. So that 8.5 centimeters here cancel out with the centimeters here. And we get into the units of students. So this is going to be a simple division problem. 570 divided by 8.5. And I get a very large number, but we are going to round it properly. So 0.5882 whatever students. But we have to round this to a whole number, obviously, because you can't have a 0.05 of a student. So this is going to be equal to 67 students. Okay, number 15, a 1 degree increase on the Celsius scale is equivalent to a 1.80 degree increase on the Fahrenheit scale. Okay, so that's conversion factor. So 1 degree Celsius is equal to 1.80 Fahrenheit. If a temperature increases by 48 degrees Celsius, what is the corresponding temperature increase on the Fahrenheit scale? All right, so we're basically just converting Celsius to Fahrenheit. So we have 48.0 Celsius, again over 1 if you want this to be a fraction, times, and then we're going to use the conversion factor of 1 degree Celsius for every 1.80 degrees Fahrenheit. And we'll make sure that we set it up properly so that the Celsius units cancel out with each other because they're on opposite sides of our fraction. And we're basically just going to take 48 times 1.8. 48 times 1.80, I get 86.4 Fahrenheit. And then we're going to keep it at 3 sig figs, seeing as this has 3 sig figs. So our final answer is just 86.4 degrees Fahrenheit. That's it. All right, we are almost there. We're getting there, okay? Number 16, convert the following. 0.044 kilometers to meters. Conversion factor is there's 1,000 meters in 1 kilometer. So we're going to take 0.044 kilometers, and we're going to, I guess we'll do this properly. So 0.044 kilometers, and we're going to times that by 1,000 meters over 1 kilometer. So kilometers cancel like this. And we'll get our answer here. So 0.044 times 1,000. We get 44 kilometers. Okay. I'm not going to do all of these ones because they're just basic metric conversions. Okay, so I'm going to let you do the rest of those ones there. For this one, number 17, I'll do the first one here just to help you out. 15 cubic centimeters to liters. Now this one might seem a little bit weird, but remember, okay, this is important to remember. 1 cubic centimeter is the same thing as 1 milliliter. So this is essentially 15 milliliters, and they want us to convert that into liters. And there are 1,000 milliliters per liter. So for every 1 liter, there are 1,000 milliliters. Okay, it's gonna look like that. So basically just take 15, divide it by 1,000, and we get 0.015 liters as our answer. All right? Okay, again, I'm going to leave these other ones to you because those are pretty simple, but if you have questions on those, let me know. All right, last questions here. 3.4 density. Gold has a density of 19.3 grams per cubic centimeter. What is the mass of a 27 cubic centimeter sized nugget? Okay, so we're going to use dimensional analysis to do this, but we have 27 cubic centimeters of gold, which is a volume. We'll put that over 1. Okay, so there's what we have. And the density here is a fraction, and we're gonna use this to do some converting. So this is 19.3 grams. Okay, 19.3 grams over 1 cubic centimeter. So this fraction can be written to look like this. Okay, and we'll see that we have cubic centimeters on the bottom of our fraction and cubic centimeters on the top of our fraction. So those will cancel with each other. So we're just going to take 27 times 19.3. We'll get 521.1 grams. And then we are going to round this to 2 significant figures. So keep the 5 and the 2. The 1 will keep the 2 a 2 and round down to a 0. So it's going to be 520 grams for our final answer, rounded the right number of sig figs. All right. Number 19, what is the volume in cubic centimeters of a sample of cough syrup that has a mass of 50 grams? And they tell us the density of cough syrup is 0.950 grams per cubic centimeter. So this one basically is just like the number 18. We're starting with 50 grams. We're converting to cubic centimeters. There's the conversion factor. Pretty much follow number 18, do the same exact thing, just different numbers, okay? If you have a question on it, though, let me know. So let's keep on moving here so we can get done. How does density vary with temperature? This is directly from the notes. Remember, though, that density and temperature are opposites. So if temperature goes up, density goes down. If temperature goes down, density goes up, okay? That's all we're going to say. So we'll say that density and temperature are opposites. If temperature increases, then density decreases. And if temperature decreases, then density increases. All right, number 21, what determines the density of an object? So the density of an object is its mass divided by its volume. So we can say that the density of an object is determined by the object's mass divided by its volume. No apostrophe there, and we do need an apostrophe there. Okay. Number 22, what is the mass in kilograms of 14 liters of gasoline? And it says, assume that the density of gasoline is 0.680 grams per cubic centimeter. All right, so this is just going to be another conversion problem. We're starting with 14.0 liters of gas, and we can do this over 1. And we need to convert this into kilograms, okay? Now, this conversion factor here gives us cubic centimeters per gram. So the volume in this conversion is cubic centimeters, and the volume that we're starting with here is liters. So those are not the same. But remember that a cubic centimeter is the same thing as a milliliter. So if we can convert our liters here into milliliters, we then can use this conversion factor to go from milliliters to grams, and then we can go grams to kilograms because a kilogram is just 1,000 times bigger than a gram. So we're going to set it up look like this. Okay, so the first conversion we're going to take is 1,000 milliliters per 1 liter. And then this will cancel out our liters and get us into milliliters. Once we're in milliliters, then we can use the density that we're given. So we're going to have it as 0.680 grams over 1 milliliter. Okay, now again, I'm not writing cubic centimeter because a milliliter and a cubic centimeter is the same. So this density given here, I'm writing it like this, 0.680 grams over 1 milliliter, because I want the units of milliliters on the bottom of our fraction for our density to cancel with the milliliters that we have in the previous part. So that will get us, that will get us into grams. Then from here, we need to convert into kilograms. Okay, and the last conversion is for every 1 kilogram, we have 1,000 grams. Okay, and the grams will cancel with those grams. So we will be in the units of kilograms. And then once we do all that, all we got to do is do the math out. So we're going to take 14.0 times 1,000 times 0.680 divide by 1,000, and we get 9.52 kilograms as our final answer. All right, last question here. Number 23, a balloon is inflated to a volume of 2.2 liters with 6.49 grams of chlorine gas. What is the density of chlorine gas in grams per milliliter? So they want us to find a density. We know that density is equal to mass divided by volume. The mass we know is 6.49 grams. The volume is 2.2 liters, but they want the density in grams per milliliter. So basically all we need to do here is take our liters of 2.2 liters and convert these into milliliters. So we're going to convert the liters into milliliters, and then once we have them in milliliters, we'll take our grams, divide by milliliters, we'll get our final answer. So remember that there are 1,000 milliliters per every 1 liter. Okay, so we're just going to basically take 2.2 times 1,000. This gives us 2,200 milliliters. So there's our volume in milliliters. And then from there to do our density, density is going to be equal to our mass, which is 6.49 grams, divided by our volume, which is 2,200 milliliters, since they want it in milliliters. And we'll get our answer. So 6.49 divided by 2,200, we get 0.00295. It's going to be grams per milliliter. And I think we need to round it to 2 significant figures because this 2.2 has only 2 sig figs, and currently this is 3 significant figures. So 2 sig figs Keep doing that on accident. 2 sig figs would be 0.00, and then this 9 is going to round up to a 10, which will round the 2 up to a 3. So it'll be 3, stop doing that, 30 grams per milliliter. So 0.0030 grams per milliliter. That is our final answer. That is the density that they are looking for. All right, guys, that is it for this whole review guide. I know that was a bit long. I'm glad that you stuck with me if you did, and hopefully that helped answer any questions that you had. But as always, if you still have confusion or still need more help, reach out to me, email me, chat with me in person, or, we can always do a tutoring session over Google Meets. All right, guys, that's it for this chapter. Good luck in your test. I'm Mr. B. I'll see you in the next one. Bye.